So now you have to tell me the slide number, and then remember it's a 10-minute talk, so it's gonna be super fast.
Yeah.
And
can I forward the slides or
no? You have to say the slide number or next slide.
Okay. Okay. Then hello, I'm Felix Meggendorfer from the Max Planck Institute for Physics in Munich, and I talk about the first experiences of our neural network set vertex trigger in the BAL2 experiment. So yeah, the BAL2 experiment is located at the Supercake B site in Japan, in Tsukuba. Supercake B is an asymmetric E+E- collider at the gamma 4s resonance for the B-meson pair production. And yes, so next slide, please. Oh, yeah. So this is the BAL2 detector. It's about 7 meters tall. And I just highlighted here the detector parts or the sub-detectors, which are part of the layer 1 trigger system. So the innermost is the central drift chamber, where our neuro trigger is working. Then comes the particle identification system, which consists of the time of propagation detector and the Erigal ring image Cherenkov detector at the end caps. And we have an electromagnetic calorimeter and then the K-long immune detector at the outermost. So on the next slide, I wanted to motivate a bit why we need the neuro trigger. So in the plot, you can see the set vertex of reconstructed tracks, and set is going into the beam direction. So as you can see, most events are coming from the interaction point at z equals 0, but we have a lot of background coming from outside of the interaction region. And since the neuro trigger is a track trigger, we can actually filter on those on this set vertex. Next slide, please. Yeah. So this is a data flow diagram of the trigger system. So on the left side, we can see all the sub-detector trigger systems, which feed their information forward to the global decision logic, which then finally decides if a track is kept and forwarded further to the high-level trigger or not. And until the global decision logic, everything is implemented in hardware, and just the high-level trigger is then implemented in software. And there, the first reconstruction is done, and then finally some more filtering, and then the events are stored. On the next slide, I want to zoom in on the data flow in the CDC. So actually, each of these gray boxes represents a specific hardware step. So dedicated hardware. So in the drift chamber, we have two types of wires. So we have the axial wires and the which are straight, and the stereo wires, which are slightly tilted. And when we combine the information of those two, we can reconstruct the 3D information of our hits. Those wires are then, one back, please. One on slide 5, please.
Which slide?
Slide 5. Yeah, okay. So then we group those wires into superlayers, into 9 superlayers, where we have 5 of those axial superlayers and 4 of the stereo superlayers, which are then input to the track segment finder, where we look for track segments. And the axial ones are then forwarded to the 2D finder, and the 2D finder finds 2-dimensional tracks in the cross section of the detector, and then the 2D finder results and the stereo track segment finder results are forwarded to the neuro trigger. So now on the next slide, there's a cross-section of the CDC shown. And there you can see the axial and the stereo layers. In total, we have 56 wire layers. And now we look within each super layer for this track segments. On the next slide, please. There you can see the pattern we are looking for. So this is the first step of background suppression. So whenever four out of 5 wires or wire layers in one super layer are firing, then a track segment is made. And from a track segment, we store the position of the green wire in the middle, the priority wire, the time information of the priority wire, and actually the left-right information based on a lookup table, whether the track passed on the left or on the right side of this priority wire. And on the next slide, we use then the 2D finder with a Huff algorithm to find the track parameters. So I think this is well known, since it's an old but quite effective algorithm. And when we then found a 2D track, then the neural trigger gets activated on the next slide. Slide 9, please. Yeah. So the neural trigger consists of a neural network with 3 layers. So we have one hidden layer, and we have 3 input nodes for each of the 9 super layers, a total of 27. Then we have 81 hidden nodes and 2 output nodes. For each super layer, we have as input angle alpha, which is between the track and the super layer, the crossing angle between the track and the super layer. We have the drift time of this priority wire, which gets a plus or minus sign depending on the left or right information. And we have the phi rel, the blue one, which is delta phi relative to the 2D track. So for all axial stereo layers, this is 0. And now on the next slide, we see the results from the hardware. So this is actually the delta set resolution plot between neuro tracks that we found and reconstructed tracks. And we get from our Gaussian fit, we get a standard deviation of 4.2 centimeters in the fit, which is quite good. So now, on the next slide, we have a look at the possibilities we have to reject events or tracks. So first, we have a very simple trigger logic. Every track that is coming from outside of 35 centimeters around the interaction region is rejected. So on the left side, we see the same plot as from the first slide. And on the right side, we actually see the set vertex of the reconstructed tracks that were rejected. So first, the background rejection works. So this peak is about the same height. But we also see a lot of events that are rejected that are coming from the interaction region. So this can be explained by the fact that the acceptance region of our neural trigger is restricted. So when we look now on the next slide on the cosine theta distribution of those tracks, we can see the acceptance region of the neural trigger is within the red bars. And when we now do the rejection, we can see that most of the rejected tracks are then coming from outside of the acceptance region. So the peak in the middle, unfortunately, we cannot see in the neural trigger. We cannot handle correctly. So we're doing quite fine, but we still have those tracks at the bottom. So on the next slide. Yeah, we have those false negatives where we reject, but we are actually, we should not reject. So this is still something that has to be understood. So on the next slide, I come to the conclusion. Yeah. So with the neurotrigger, a great background reduction is possible, but we still need to understand where those false negatives are coming from. And the next step is then to move from a track-based to an event-based trigger decisions. So we can get even better and implement two-track trigger algorithms. And then an outlook. So tomorrow, Sebastian from our group will talk about improving the 2D finder to a 3D finder, also with an Huff transformation. So this is also quite an improvement and very interesting. Thank you.
Thank you very much. Unfortunately, I think we have to keep going because the time is wasted some time. So I don't see any hands raised, but the talk is recorded and there can be discussion later. So thanks very much.
Okay.